Sorry for the delay. Warm greetings to everybody. So, how many of you are undergrads here? Yes. Four of you. And PhDs, anybody? Okay. So, I guess it's mostly MTech first year students. Yes. And so you probably already had a few classes with the other core courses, fluid dynamics. Excellent. So you didn't have a full-fledged class. So this is also one of the core courses for the MTech, as all of you know. And aerospace engineering is a highly multidisciplinary area, and it typically has intake from many different disciplines, because of which we have this very strong course foundation, wherein we typically try to take up to speed the non-aerospace BTechs onto the same level as what the aerospace BTechs do. So that being the case, most of this course is at an undergraduate level, so which is why it was open to the undergraduates, and even in the previous years we have had a few undergraduates crediting this course quite successfully. So those of you from an aerospace engineering background, can you just lift your hands? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need to apologize to you that this will be probably a repetition of a lot of things that you have learned, but hopefully a revision, and every now and then I will be also bringing in certain aspects of research. So to tell you as a class as a whole what is the current state of the art and how the different directions in the aerospace industry as far as structures is going is moving towards, so that you get a flavor for the current status, so to speak. And also to introduce myself, I am an aerospace engineer right from my bachelor's level, so BTech, master's and PhD has been in aerospace. So if you have any issues in understanding not just structures but anything related to flight vehicles and the other courses that you are also taking, in terms of how it interfaces with this, so I would be happy to answer that. The whole course I would like to make it as interactive as possible, so that the learning process is enabled much better rather than just you listening to a lecture. So anytime feel free to just raise your hands and talk, or even without that you just go ahead and shoot your questions, comments, whatever, and we will see how we can address those things. There might be certain things which I might want to cover a little later, which you might ask, but so in those cases I'll probably postpone it a little bit so that the suspense in the story is not broken. So I'll try to handle it that way. And so we saw the aerospace engineers, so let's probably also take a look at what other backgrounds we have over here. So let's come onwards and we'll see how we can connect the iPad over there. So we saw AE. Next we typically have civil engineers. So how many did I count? The aerospace once again, please, out of 10, I guess. 2, 3, 4, 5, 6, some 8 and 10. And then from civil engineering background, okay, it's reducing year by year. It's going to be unique. What's your name? So usually we have quite a few civil engineers, but it's probably an exceptional year. Next, mechanical, I'm sure there are quite a few, probably more than aerospace. 1, 2, 3, 4, 5, 6. What's the doubt? Yeah, at the bachelor's level, I'm just asking at the bachelor's level. You did the master's in aerospace, mechanical. I see, materials, okay. So mechanical, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Matching data. So materials, only one WEC, any electrical related. Only two. How many UGs were there? 4, is it? Have I left out any branches? Yeah. Production. Only one for production? I guess everybody is covered here except the TAs. So I guess everybody is covered over here. So the reason why this is important is for you to see amongst your own classmates how there is a varied distribution across the different disciplines that we have over here, and that is a reflection of what it is in the aerospace industry as well. If you look at even the regular engineers who are working all the way for new recruits as well as all the way about to the CXO levels, you will see that there are people from various backgrounds as far as their bachelors are concerned who are into the aerospace industry and doing really well. And that's the case even not just in the industry but also in academia. If you look at IISc, for example, if you look at the faculty profiles, you'll see that quite a few of them are non-aerospace BTechs or BEs. So, which means that all of you are most welcome here and don't feel out of place. Obviously, you've chosen this out of a certain interest, certain motivation, maybe a certain knowledge about what is involved in this. So, I'm sure that will match those expectations, if not beat them. So that's the reason why I just wanted to know this. Yeah, the thing is, many of you would have been exposed to structures, except probably the WEC. You had any course on structures? No, because typically when we have research interviews, we have these 4 disciplines: structures, propulsion, we have aerodynamics and controls. And in controls, navigation and guidance is included. But what typically happens, and the students are asked to choose which research committee they want to attend the interview in. And sometimes in the structures committee, we get the EC people, though we would typically expect them to go to the controls panel for the interview. Later on, we found out that they got confused with data structures. So computer science and CE, ECES, W people started coming to these interviews. So this terminology, you might find similar terminologies in other places, but what we mean by structure is essentially certain materials which are brought up in a certain geometric configuration in order to be able to bear loads. And when you're talking of loads, primarily we're talking of mechanical loads. But it could be thermal loads, it could be loads coming from the control systems, etc. So there could be the engines, which is a propulsive load essentially, and the aerodynamic loads getting redistributed in different fashions. We'll look at all of them in detail later on. But this is essentially what this structure does. So as I already mentioned in these sentences in an implicit way, there are 2 important aspects to this. One is the material that you choose. And usually just a single material will not work. Many of you know that in 1903 we had the first recorded, Western history recorded propulsive flight where an engine was used. Prior to that you had balloons and you had glider flights, KD and Otto Lilienthal and various other people have pioneered the work. Leonardo da Vinci and we have the concept of the Pushpak Viman in the Indian scriptures as well. But in terms of the recorded history, how it has actually developed as a science and engineering, it's a fairly short history compared to automobiles or many other fields. Are there any automobile engineers, automotives? No. So, but I guess many of you mechanical in terms of machine design and things like that, you probably be aware of certain aspects of vehicle dynamics, etc. So what we are going to first do is to understand structures from this perspective of what each of you think, being from the different disciplines, so that we are on the common page in terms of it will not be as funny as data structures, thinking that this is what we got here. But though we use a lot of data here as well, and we structure it in a particular way. So we use those tools, but that's not the basic or the main content of this particular course. So just to bring everybody on the same page, as I said, there are quite a few differences between the way we use materials as structures in the case of, let's say, non-aerospace constructions. Civil, you would see a lot of different constructions, maybe bridges, roads, or buildings, and so on and so forth. And similarly, in the case of mechanical, the machines and the vehicles, surface vehicles, which could be vehicles on the road, or it could be on let's say on the rails like trains, or you could also have vehicles which are typically on the waters, like the boats and ships. Though naval architecture is a separate discipline, there's a lot of commonality in terms of how the vehicles move on the surface. Okay? So there's a little bit of extra motion that you have in the water compared to probably on the roads. Even on the roads you have these shock absorbers and the tires, because of which there is a slight motion in the third direction. But you would see that it's far more in the aerospace, where the vertical motion of the body, the flying body, is much more significant than any of the other examples. So just to bring everybody on the same page, we'll try to look at certain differences that are there in these structures when applied to different areas. So the first thing that we will probably look at is in terms of the material choices. So what all materials are typically used in aerospace and civil, etc., etc. So I want to make this a little more interactive. But just to give you the background of aerospace, you see that in the early 1900s and 1910s, 1920s, those probably 2 or 3 decades, there was a lot of use of what we today call as composites, and something which is very, very common in the aerospace industry, but in a natural sense, because wood was used very extensively, fabrics were used. Fabrics are essentially, as you know, fibers which are woven together. So in a sense that is also a component of what goes into a composite as we know today. But so we have done a full cycle now in the last few decades. In fact, almost for 40, 50 years, if you look at historically, composites have almost taken over many of the other materials. But we started with wood and cloth, and in between we went into aluminum alloys and many other alloys, including steel to a very small extent, titanium alloys, magnesium alloys, etc. So we will cover a few of those things in detail later on, where they go, why they are needed, why not some other material, what is the advantage of these materials in particular parts of the aerospace structure as opposed to any other. So that's essentially the way we will structure this whole course. So that's as far as the materials are concerned. Then there is the other thing about the geometry. This is again very, very critical, that if you look at the geometry of aerospace structures, I'm not talking the overall aircraft or the helicopter or let's say a launch vehicle or a missile, a satellite. So any of these flying bodies, including lighter than air systems like hot air balloons, stratospheric airships, etc. They have a certain overall geometry, which is typically dictated by the aerodynamics. So the aerodynamic design requires certain shaping in order to minimize the drag or maximize the performance in some way. So you'll be looking at a lot of those details in flight dynamics, and flight and space mechanics is a course where many of these things will be stitched together, so you'll be looking at those aspects over there. But when I say geometry here, I'm talking of not the overall geometry, but the geometry of individual components which make up that whole structure. And there could be many components which are non-structural. In other words, their primary job is not load bearing. They could be something else, let's say the avionic displays, etc. And there could be certain other things like the parts of the wing or the parts of the stabilizers, what we call as the horizontal tail and vertical tail, the control surfaces that are there. So many of these things, and the fuselage, all of these will be made out of structural components. and those structural components have certain geometry in terms of their shaping and the sizing. Because when we talk of geometry, we have two aspects to it: the shape and the size. So the shapes could be in the form of beams, it could be in the form of plates or shells, and again within beams there could be various categories like thin wall beams, thick wall beams, or solid beams, hollow closed cell beams, or it could be open section beams, etc. Again, in terms of plates, when you move with the initial curvature, you could have different kinds of geometries and small thin plates, thick plates, plates which are sandwich in nature, etc. So there are many possibilities. If you don't understand any of these words or terms that I'm using here, don't worry, absolutely. We will revisit each and every one of them and try to understand it in a very basic sense. But here I'm only trying to give you an overview of what to expect in this particular course. So the geometrical differences between these different areas are very critical. Then you also have, in terms of the kind of loads that are typically applied on each of these kinds of engineering structures. Of course, there's a lot of commonality also, because at the end of the day, it's the same physics and math that you're using everywhere as far as the design is concerned, as far as the analysis is concerned, even in an experimental study of fabrication, the manufacturing, the testing, everything involves a lot of science and math, which is most of the time not even the undergrad level, but even the high school level. So essentially it's an application of that, and sometimes we try to make it sound complicated by using all this terminology. If you break open the terminology, you will see that this is fairly straightforward. So that's essentially what we will try to look at from a perspective of very basic terms, though we will continue to use these because you have to get familiar with this. As aerospace engineers, when you graduate, you will be a master's in aerospace engineering or PhD in aerospace engineering, BS with probably a minor or whatever, a few courses in aerospace engineering. What you are essentially looking at is to have this overall idea of how these things work. And those of you who are MTechs, because that's the majority of the class, who are not going to be specializing in structures, for them also this course is extremely important, because these days a lot of the work that goes on is interdisciplinary. Even if you go for very deep research, unless and until you are aware of what are the other aspects which are affecting your problem, let's say the aerodynamic loads, how they behave, how they change, etc. You're going to be working in ivory towers of no consequence to the real world in terms of its actual applications. So it's very critical that each of you, irrespective of whether you're planned or not planned to specialize in a particular area, to get this breadth, because as important as the depth is the breadth of vision that you should have, so that you know the deep things that you're going to be working on, as probably some of you will go into PhDs or postdocs and as faculty members. The deep research that you go to should be applicable somewhere in the real life, and that is possible only when you work in large teams, and those teams will involve people from different disciplines, and you should be able to talk with them and understand what they are conveying, which will involve a lot of this terminology. So if you just go a little skin deep into that, then that's good enough to make sense of what is going on. So that's the way this course is structured. You will not find too much of mathematics in this course. It's more of a qualitative sense of understanding, but we will, towards the second half of the course, involve a few mathematical equations at a fairly basic level, which even the undergrads can understand. As I said, the whole course is structured at the undergraduate level, so we will see how that can be handled as well. But if some of you have who are going to be specializing in structures, would like to interact with me outside the class or even at the end of the class on deeper subjects related to aerospace structures in particular, then I'd be happy to share whatever I know of, and if I don't, I will probably come back to you in future classes. This whole interaction has to be a learning experience not only for you all, but for me as well. And I found it to be so in the case of quite a few batches in the past where quite a few students who come up with brilliant questions which are quite thought-provoking, and that leads to certain better or deeper understanding for all of us, and probably would open up certain research avenues as well. So feel free to interact in that open way. So let me come to this, and let's start with civil engineering. So this one of you. So who's this? Yeah. So can you just mention what is the primary difference that you see in each one of these areas? Material, geometry, loads, maybe even design, let's say. So design in all of these areas. Doesn't matter whether you're right or wrong, but just your basic understanding of what could be the primary differences of civil engineering structures, well, let's say a building, for example, or a bridge, compared to typical aerospace structures.
So when we start designing the basic problem, what is what? That is loads. That is a basic problem. For example, if you design a bridge, your first question comes to mind that how many people or how many vehicles will come to a bridge? What is the utility factor? How much footprint there it is going to be used? So load is the primary thing. Then comes to the site conditions and other things. Based upon that, which is the material, whether it is a steel bridge or concrete bridge. Then comes the geometry. It may be an arch bridge, it may be a cable supported bridge. Based on that, then we started designing the further process.
Sure, yeah, that's the overall process, and the process is somewhat similar in all places. What I'm trying to understand is what are the typical differences in the kind of materials that you use in civil structures and aerospace structures. You may not be exposed to all of the aerospace materials, but what's your understanding or a guess or some popular reading that you have done or videos that you have seen? From that, what kind of materials are used in civil which cannot be applicable, for example, in aerospace, and what kind of materials which are used in aerospace are typically not used in civil, and what could be the reasons for that?
Actually, the basic material which we using in civil engineering is two basic: concrete and steel.
Yeah. Okay.
The problem of concrete is it's very brittle. It has a good compressive strength, but it's almost negligible tensile strength.
Okay.
And in case of steel, the problem is it's very weak in shear and it's quite heavy. When you're going to use it for any aircraft structure, self-weight is also it's a significant. It plays a significant role for the lift and generate. So if you use steel and steel structures, I think it will be difficult for the structure to sustain the flight. That's it.
Okay, good enough. Those of you from the aerospace engineering background, any one of you, how do you see the aerospace materials being different from civil? Like, for example, you mentioned concrete, you mentioned steel. There's reinforced concrete where you have the steel reinforcements within the concrete, etc. So, why do you think those cannot be used on an aerospace material? What is the reason? Yeah.
In aerospace, we look for high specific strength. That is, the weight is the major determining factor in aerospace. But in ground structures, we are not considered about weight, but rather it should never fail.
So when you talk of material, when you talk about the weight, what parameter of the property of the material dictates that? You mentioned specific strength, we'll go to that a little later, so that we'll take everybody into a picture. But purely from a weight point of view, what is the material properties? Is the mass density, right? So you typically, let's call it rho, for example. So the rho, you want it to be fairly low over here. It's not that you want the civil engineering structure to be heavy, but in most cases this is on par, or it's not a primary motivating factor, or it's lower in priority compared to many other requirements. Okay, And she pointed out a very important thing about specific material properties, which is very, very critical. We'll spend quite some time on that, maybe over an entire class on that. So she mentioned specific strength. So similarly, you have something called specific stiffness, which is also very quite commonly known. But there's also something called specific stability, which most people are not aware of. And these three play a very, very critical role in which materials you typically choose. So you would see that these are the primary reasons why you would not use some of the materials being used in civil engineering on aerospace structures. So by itself, concrete might be quite strong, it might be quite stiff, especially once it is reinforced with steel, it could be fairly strong. But what we are interested is not in absolute values, as she pointed out, it is the specific values. So what we mean by these specific values is to take into account this density. So in other words, typically you're talking of strength parameter, which is again depends on the material. Certain materials might yield, certain materials may not yield. But just for commonality, let's call it the ultimate tensile strength, for example. So what we're talking of is that sigma u divided by rho, because rho has to be very less. So your sigma u by rho, which is what she called as the specific strength, you want it to be very high. And that is a parameter which will fail in the case of, the test will fail in the case of the civil engineering materials like concrete, reinforced steel, etc. They might have a fairly large sigma u, but the fact that they also have a large rho makes this ratio not so high, and there are other candidate materials which are typically much better choices in aerospace. As we already talked about historically, started with wood and fabric, and went on to aluminum alloys, which are fairly light compared to many other metals, and then gradually we moved on to composites, and all of them has happened primarily because of this and similar reasons. Like the other that we mentioned is in terms of the specific stiffness, which is the Young's modulus divided by rho, the mass density that we have. So that's another factor. Right now I'll not talk about the parameters involved in the specific stability. We'll come to that later on. We'll derive that, and we'll talk about that a little later. So yes, sigma u is the ultimate tensile strength. So in other words, if I take a specimen like this, right? So and I load it in what is known as a UPS machine. So you are basically, what you're doing is you're applying an axial load, and then you're trying to pull it apart. You notice in terms of the load, you measure what load this actually failed, right? So that load divided by the cross-sectional area gives you the ultimate tensile strength. To put it in a very simplistic way, we'll come to a little more rigorous way of defining it later. But so that's essentially what it is. So a stronger material would require for the same cross-sectional area much larger force to be pulled apart. So it's essentially the normal force to the cross-section divided by the cross-sectional area. It could be either the original cross-sectional area, or in certain ductile materials, for example, as you keep pulling, the cross-section will keep shrinking, right? So it could be what is developing over there. So there are very many different ways of looking at it. We will come to all those details later. But for now, it suffices to know that it's essentially a stress at which the material fails. And stress is defined as the force per unit area. We will go into matrix definitions and tensorial definitions, etc. later. But for this beginning, that's good enough. Right? So, and before you ask what is the Young's modulus is essentially, so this is a brittle material, so I probably cannot explain it using this. But essentially, if you have, let's say, a wire like this, and I'm trying to pull this, there is going to be a small change in length that is going to happen. It will happen with that as well, but the change in length will be very, very small. In other words, what we call as the strains that it undergoes will be very small. So the strain that we're talking about is a change in length divided by the original length. But that's just one part of the strain, what we call as the normal strain. There are many other aspects to it, like shear strain, etc. And matrix way of looking at it in a three-dimensional structure. So this E is basically saying that for most materials, this behavior between the stress that we just described, that is force per unit area, and the strain, that is the change in length per unit length, these two are linearly related to each other, and that's a material property. So that's what we call as the E or Young's modulus, but that's again a very simplistic way of looking at it, because there are many gradations to it as we go to composites, etc., where properties can be different in different directions, and you can use hybrid materials where properties will vary from point to point, what we call as non-homogeneity, etc. So all those complications for later, but basically that's all there is. You're applying a force, you are seeing certain deformation taking place. So what is that force divided by area? That's the, for now, that's what we call as the stress, because this term will be repeated quite often. And similarly, what is the change in length to the original length? That is the strain, or more specifically normal strain that we're talking about. And the way these two are related to each other is a purely material property, at least for small strains or the initial small values of the load. And therefore, this is a constant. And that constant, material constant, just like density is a material constant, and then that ratio is what we call as the specific stiffness. Why that is important, etc., we'll look at it in a little more detail. So that's as far as the civil engineering materials are concerned. Again, between the aerospace and the civil engineer, we can also talk about the other differences that exist. What about the geometry? If you look at the geometry of typical civil engineering structure, we're not again talking of the entire building, but the parts that it is made out of. Let's say the foundation, then you have the columns, then you have the beams, etc. So what kind of geometries are these individual components? Do we have similar components in flying vehicle? And if we do, what are the geometric differences between them? Anybody?
The geometry is very critical to deal with aerospace applications.
Okay.
For instance, if you take a gas turbine engine, so the design of turbine is a very critical component because it has standard centrifugal stresses as well as the thermal stresses. So those kind of stresses would not be dealt with civil engineering applications mostly. For instance, if you take concrete or stainless steel, they won't be subjected to, they may be subjected to stresses but not thermal stresses. So in that case, geometry is very critical aspect, because we have to, the design of blades are dictated by aerodynamic constraints or by design parameters that we analyze. So it all comes in the picture.
Okay, so it's correct that geometry plays a very critical role, but what I'm looking at is not getting into these other aspects. We'll cover them one by one. Purely now I'm talking of geometry, and as I said, geometry involves two aspects to it. One is the shape, and the other is the size. Right? So I want to see what kinds of shapes are typically used in flying vehicles, which are not usually used in civil, or the other way around as well. So I would like to give perspective on that.
So in aerospace, as far as shape is concerned, we go for thin wall structures which are hollow in nature because they contribute to this aspect of lightweight. So we use thin wall, hollow materials and some geometries for aerospace structures, whereas in civil, I think most of the geometries are solid.
Yeah, it's an excellent point. So again, the reason is very similar to what we're talking about here. We want to reduce the weight to enhance the performance, and very soon in your flight and space mechanics as well as your fluid dynamics, you will see the actual technical reasons and the equations involved why this is so critical. Okay, but for now, it suffices to say that one way of reducing weight is by using lighter materials which can offer similar values of sigma u and e as the materials currently being used. So the research is always towards either reducing u or increasing this so that the ratio actually goes up. Okay, so we're not interested in each of their absolute values, but that particular ratio. And one way of doing it is, of course, to reduce the overall weight of the structure is by changing the material itself to go to better superior properties over there. But the other way of doing it, as we pointed out correctly, is the thin walled structures that you can use. So you see that typically the beams that are there or the column that you see at the corner of this room, those are fairly solid cross sections and fairly large, and typically you have rectangular cross sections over there, which are solid, not hollow. And even if they were hollow, they would not be usually thin walled, they would be fairly thick walled structures. So by doing that, what we are trying to do is again reduce weight, but at the same time, it has to be able to bear that load. So it's not at a risk of reducing the load carrying capability, but an ingenious way of doing it so that you redistribute that material in such a way that where it is needed most, you have more of the material. Where it is not needed, you remove the material from there. So to put it in an example form as an illustration, if you, many of you who have taken strength of materials course, anybody who has not taken strength of materials course, electrical, okay. So don't worry about it. We'll get those concepts also, the important concepts in place over there. But so those of you who have taken strength of materials, you know the beam bending problem, for example. You have what is known as a bending stiffness, which is typically written as E times I, the Young's modulus times the moment of inertia. Now the Young's modulus is a material property. The moment of inertia is a geometric property, in particular the cross-sectional geometric property. And you know that the second moment of inertia, which many of you from a mathematical point of view will be aware. So second moment of inertia of any geometry is basically that the same amount of material, if you redistribute in such a way that they are farther away from a so-called center, which we will define in more specific terms later on. But the farther you move it out of that center, the better capable it is. In other words, instead of having the same material all lumped up together in the center, you are trying to move it apart so that you're not probably reducing the weight in an overall sense, but you are trying to make it even more effective in load carrying capability. And you could also even scoop out that material in between, which is undergoing much less stress, and therefore you're having a much more efficient structure. That's how we come up with a, let's say, thin wall structure. So that's as far as the example that I talked about is typically useful for torsion. So when you're trying to twist the structure, so you're trying to scoop out the in-between material because that's not carrying much of the stress, and we'll see the reason for that, the equations for that later on. But the outer material is taking most of the stress, and therefore why have material wasted over there, because that's adding to the weight penalty that you have. Of course, there are going to be issues because of that. In some sense, it's going to collapse in a particular way, etc. But obviously, your design has to be ingenious enough to take care of that. So that's how we look at the various aspects which affect that. So that's the sizing. Now, in terms of bending, which we started illustrating, you typically have what is known as an I-section beam, for example, where you have flanges, and this there is something called a web. So essentially, it's the shape of an eye, and that eye cross-section usually is very good at taking bending in this particular direction, because most of the bending happens by taking loads which are tensile and are compressive, and that is happening farther away from what we call as the neutral axis. And when we move material out, you are essentially making it more efficient. So once again, a geometric jugglery that you are doing in order to arrive at a more efficient solution. So that's as far as the geometry is concerned. So thin wall. So let me just write that down. Thin wall sections, and whether it's a beam or it's a plate, we typically have thin plates as opposed to much thicker plate form, like in the case of the foundation of the building, etc. So that's what you would have. Whereas here you have mostly solid cross sections, which are of fairly bulky kind of geometries that you have. So that takes care of the shaping as well as the sizing we're talking about in terms of the geometry. Now let's talk about the typical differences in loads. Anybody else from the aerospace engineering who can talk about what kind of loads you find in aerospace which you may not find in most civil structures? Yeah.
Aerospace, we are specifically aerodynamic loads. While in civil, maybe the aerodynamic loads for the airports are the
Very good. Yeah, so aerodynamic loads are very critical over here. Okay, so aerodynamic loads might be important in a civil engineering structure where you have, let's say, a swaying bridge, for example. So the kind of air loads that come over there, but those are of lower priority than the much major loads which would affect the overall behavior in a greater way compared to the aerodynamic loads. So whereas here that becomes the primary load, so that's a very important point. And right there, even if you don't have the aero part of it, even the second half of it is very, very critical over here. That's a huge difference. Whereas in civil engineering structures for earthquake, seismic kind of design, you would have to consider certain dynamic aspects, certain natural frequencies, the mode shapes involved, how you could improve the design based on that, etc. But again,
I'm fine only with the structures like bridges and others that dynamic load is there's a very important, that is a basic load.
true.
Otherwise, in case of buildings or other civil structures, we can
Yeah, so it's mostly static. So that's a very, very important thing. So it's not only the dynamics is getting affected by the aero aspect of it, but even the very fact that your vehicle is actually a moving structure, as opposed to most civil structures which are static structures, and therefore the loads that are involved are predominantly static. So of course there are exceptions in both the cases, etc. We're not talking of that. You could have a balloon which is static, or in some sense a geostationary satellite is in a static position compared to the Earth's fixed frame of reference, etc. So those are all things that we talk about. But essentially, dynamic loads play a very, very critical part. And again, dynamic loads, one is from the aerodynamics, the other is also from the kind of dynamic load that is involved. It could be just a free vibration, it could be a forced vibration, it could be an impact problem, it could be a fatigue because of cyclic kind of loading. So there are many, many different ways in which the critical decision factors on the material and the geometry are made based on the kind of loads that a particular structural component is usually susceptible in its service life. Again, the service life, there are many different phases in the case of an aircraft motion. So you have a taxiing phase, then you have a takeoff, then you climb, you cruise, and you descend, and you land and taxi again. That's the simplest that you could have. When you go to more complicated systems like fighter aircraft, etc., the kind of maneuvers that it has to do, etc. And even in the regular passenger aircraft, for certain reasons, you need to handle gusts, etc. So you need to have certain capabilities in certain maneuvers that you do. The concept of what is known as the load factor comes into picture over there. We will define that a little later. So this is different from what you're familiar with. Maybe this is something that is stretching both these design aspect as well as the load. Because what happens is, as you would have observed when you're going into, let's say, some of these theme parks and other things where you're going on, let's say, many different kinds of rides, you would have experienced certain forces on the body very different from the usual gravitational force that you experience on a day-to-day basis. And this is essentially because you being belted to that seat on the ride are experiencing certain what are called as G-forces. In other words, the acceleration due to gravity is either enhanced in a positive or a negative sense, because of which you feel that gush of blood flow either in the upward or downward direction, and many other ways in which the body reacts to that. And that's essentially what's happening in the case of an aircraft almost on a regular basis, especially fighter aircraft, etc. But even in the case of passenger aircraft, there's a certain range of load factors that it goes to. So in what is known as a cruise flight, that is after the aircraft has got to the altitude that it is designed to fly at, it typically is doing what is known as a level flight, when the lift that the wings are generating should be equal to the weight of the overall aircraft. Now, that is what is called as an n equal to 1 or a load factor of 1 kind of a flight. But when it is either descending or it is ascending in an accelerated sense, you are doing certain maneuvers like a dive or a pull-up, etc., you would see that these lift divided by weight will not be 1 any longer. It could be different from 1, much larger than 1, or it could be less than 1, it could even go to negative values. So our structural components, whatever it be, a part of the wing or a part of the fuselage, a part of the tail, a part of the control surface like aileron, rudder or elevator, each one of these components you have to see under what are the circumstances under which it will face the maximum load, what is the critical case for the design. And there may not be just one, there might be a few for each one of those components, and you have to make sure that for all of those you are designing it appropriately so that in the eventuality you do not have an issue. And so when we come to the design aspect, there is something that we look at what is known as the factor of safety. Okay? So that's another huge difference that you will see. What is the typical factor of safety which is taken for aerospace structures? 1.5, yeah. Any idea why we take 1.5? What is the sanctity about this particular number? Yeah. True. So what you're saying is a correct reason for it to be greater than 1. But why 1.5? Exactly. True. But it could be even if it's 1.4 or 2, it would still be basically loads. Why did we come up with this 1.5? Right. So if it's too much, then you basically are over designing it by a very large thing. It will be too heavy. It may not fly at all. Or even if it flies so efficiently that it burns so much of fuel extra, or you take very less payload, etc. So if it's too high. If it's too low, what happens? So you could have run the risk of the structure failing under uncertain loads, because you might have designed for what you thought was the extremes in the what is called as a flight envelope, a Venn diagram, where you plot the velocity of the aircraft, or rather the speed, versus the load factor, and you see that you are taking care of all those boundaries or extreme situations. But in reality, you might have a situation which you may not have anticipated, where the aircraft faces those loads, and because of that structural component, the load is getting transferred to that, and that structural component might fail. So there is a possibility that this danger is there, so you cannot have it too low. But why 1.5 is a very funny and weird reason that in the initial stages, after we moved over from wood and clothing fabric as the main structural material, the material for many decades which was dominant was the aluminium alloys. And typically for aluminium alloys, you see the ultimate tensile strength divided by the yield strength is approximately of this order. So, and that has just carried on, even though we have changed materials, we have done lots of things, because it's not just the aerospace industry or the aerospace engineers who decide this, but there is what is known as a certifying agents. So the US, for example, is the FAA, Federal Aviation Authority. Similarly, you have EASA in Europe. In India, we have two. One for the civil aircraft, which is the Director General of Civil Aviation, which is abbreviated as DGCA. And for military aircraft, you have what is known as CEMILAC, right here in Bangalore. And so these are certifying agencies, and they have certain requirements. Unless or until you fulfill these requirements, your aircraft will not be certified. And there are also ways in which the structural components are certified, these materials that you're going to use are certified, and if it's what is known as a flight-worthy material, only those can go into making your overall aircraft structure. You cannot use those which are not yet classified as flight-worthy, and which is the reason why you see in our labs or any research labs, both in R&D institutions as well as in industry, people will be working on a lot of very, very interesting, unique things, multifunctional materials, various kind of functional graded materials, etc. But by the time it actually gets onto a flying aircraft in terms of a primary structure, it could be a few decades. That's how long it took engineers, synthetic composites, for example, to come on in a very broad sense the way it is to extensively used today. So there is a certain level of conservatism, and it's for the right reasons, because safety is of paramount importance over here, and you want to ensure that every aspect of it has been taken into account before you allow certain materials to be flown. So that is essentially the reason why there is a huge delay between the research into these materials and the actual application into flying vehicles. In small sense, we've been lucky in the recent past of about a decade or two, where we've been looking at drones, and in particular looking at smaller drones, what are known as micro-aerial vehicles or nano-aerial vehicles, which are simulating bird-like flight or insect-like flight, or even fixed-wing UAVs, etc. So there, the risk involved is not the human life, at least unless it goes and crashes onto a place where humans are habitating or whatever. But overall, the risks involved are much lesser, and there is more room to play around with newer materials much earlier than what you could do with, let's say, passenger aircraft or even fighter aircraft, which are manned with piloted aircraft. So all of these need to be taken into consideration. And this 1.5 has been a huge debate for long. Why should we stick on to that? We have composites and we have a better understanding of how the material behaves, how the structure behaves over a period of time than what we used to long back, where the uncertainty was so truly uncertain that you really needed a large factor of safety. Because 1.5 we say is large from an aerospace point of view because we want to improve the efficiency, etc. But from a civil engineering point of view or many other machinery point of view, this might actually be already low, fairly low. But there are attempts these days to look at a better knowledge-based factor of safety for individual materials, individual types of components, rather than one fixed value of 1.5 for all materials, for all geometries, all kinds of structural components. So this is something that is moving in one direction. The other thing is in terms of the design philosophy, you have two aspects. So here, of course, you have the factor of safety much larger compared to 1.5. What are the typical values which are used? Okay. Very good. Right. It's good to know. So where is typically about 1.2 used? What kind of structures? Any examples?
Storage buildings, for example, nail board storage or any warehouse.
I see. Okay.
So there is no
Not critical.
Yeah.
So
what is the logic of having the ultimate ratio? I mean, there's no ratio and use that ratio.
Yeah. So see, the design is typically made on the ultimate strength. So you want it at least not to yield. So that is the whole idea of that 1.5 ratio. Because when it yields, what happens is beyond your elastic regime. So you can have some permanent deformation that is taking place, which can change the overall shape of the structure, which affects the aerodynamic performance, etc. So it has a lot of repercussions in terms of how that affects. So it's more like typical like a thumb rule which some people took and it worked for a long period of time. So people just stick on to that. So we think that all of science and engineering is purely logic-based, knowledge-based. No, there are a lot of empirical factors and empirical equations that are used even today. You'll be surprised when the knowledge base has improved so much in terms of a physics-based or a pure math-based kind of an understanding of different systems. So it takes time for these things to change. It's not that it's not changing at all, but the pace at which it's changing is quite gradual. So the reason, as I said, is that you do not want it to get into the plastic kind of regimes, so that there is a permanent deformation because of which the overall airflow and other things are affected. And this is true for the interior structures as well, because the load transfers on to the skin eventually, because they're all connected in some sense. And therefore, if one of them fails in a particular way, within quotes, you are affecting the overall behavior in terms of the way the vehicle interacts with the ecosystem.
So but in that case, the vehicle is designed for yield, the fade is considered for yield. Then is the logic similarly applied? Because probably when they shifted from wood to aluminum, they were probably designing for yield rather than ultimate.
Right. So eventually, see, it's just you needed a certain number which is kind of which is workable, right? So when there is lack of information, because this is the very early stages of flying that this was arrived at, and very serious measures are being taken to move away from that. And there are a few exceptions that are created in the case of drones, for example, where you can have a much lesser number. So again, this 1.5 is only for aluminium. It can be very different for other metals also. So and you really do not want to design at the ultimate tensile strength and then come down to a yield, because that's also quite risky. So you want to have it even lower than that, but it's just a ballpark number. So even when it is used to design with the yield strength as the ultimate strength that you want, you will still go for 1.5 factor lesser than that yield strength to make that as your design limit load. So we have two concepts called the design limit load and the design ultimate load, and it's the ratio of that which is what we call as the factor of safety that we are designing for. So that design ultimate load, even though it uses the word ultimate, may not be about ultimate strength, it could be the yield strength. Again, it varies from material to material, because some materials, even metals, may not yield at all. So it directly has a failure which is ultimate, which is more like a brittle kind of a failure. So it depends on, for example, the carbon content in steel, for example, the heat treatment processes that you have undertaken, etc. So you will see that those significant differences can be there. But just to have one ballpark value which seemed to work fine for a lot of different structural components made out of different materials, they eventually stuck onto that. But it was too long to stick onto that. That is the main problem. Yeah. So we will visit all of these later on. So this is the design ultimate load divided by what is known as the design limit load. The DLL is the value that you are designing for. So this is the load factor that you have, and the load, based on that load factor, you would have for the different load factors how you design the material along with an additional factor of safety. So these are two separate things which are used in conjunction with each other for the safety of those primary structural components. In addition, there are certain philosophies of design. They are more advanced ones of late, but which have been used classically are what is known as the fail-safe design and what is known as a damage-tolerant design. So these are two different concepts. Damage-tolerant design is a little newer. The fail-safe design has been around for fairly long. So if you look at mechanical engineering devices, for example, where weight is not critical, you typically will have a certain level of redundancy. So in other words, the same one particular component is doing a particular job, you also put another component which is also doing the same job, so that in case one of them fails, the other will start handling the loads that are involved. So this is what is known as a redundancy or a fail-safe design. And that continues to be used in a very, very few aerospace structures where it is really critical. One of the main reasons why flight took so long to take off in terms of history, 1903 is when we had our first powered flight, is because many people were trying to do it. The wings flew apart from the fuselage, so it broke and fell apart. So that particular junction or the attachment of the wing to the fuselage is a very, very critical part, and historically that Now, the way the wing is joined to the fuselage, there are of course many different specific techniques, and some are proprietary to the different companies, but usually we will see in passenger aircrafts there is a redundancy in that, so that even if one of them fails, the other will still hold on at least until the pilots are able to safely land the vehicle for any maintenance or repair or overhaul to take place. So that is what you typically have an example. Another example is typically in landing gear struts. In some cases, you will have the fail-safe design where you have a redundancy, so that even if one of the structural components of the landing gear fails, the other structural components will be able to handle it. Of course, it might also fail eventually by the time the aircraft lands, but at least there is no fatality or damage done to major damage done to the aircraft, and you can probably replace that part and or overhaul it in some sense. So those are the different aspects that we look at. Yeah. Very good point that you brought out. So there's been a classic difference in the way the wings have been designed. And you would have seen pictures of older aircraft, many of you. We had what are known as biplanes, where there are two wings which are attached to each other through what are known as ties and struts. This terminology again has stuck up, even though we no longer are tying these wings. But essentially, what a tie means is it's like a cable like this, which, as you know, can take only tension, it cannot take compression. So it fails very easily in compression. So where you know certain components are going to be loaded only in tension, there's no chance of it going under compression. This is a lightweight, efficient way to do things. Similarly, what are known as struts, which from a purely mathematical or physics point of view are like columns, which are always taking compressive loads, so you have those struts. So these two wings of a biplane are typically attached by those strings and rigid members, which are called as struts, the ties and struts. So now, when we move away from the biplane, in fact, there were even a few triplanes where you have three wings which are attached to each other. Conceptually, it was very interesting, a very ingenious way of doing things at that point of time. But what people eventually found is that one, of course, these struts and the ties were taking up a lot of weight. The other is that the ties and the struts that you had a shape which was not aerodynamically efficient, so that the drag that they caused was very large. So, but the advantage that they had is that now you have smaller wings. You have broken up into parts, so the way they are attached to the fuselage, you don't have that large loads coming up. Because if there's one single wing, the entire weight of the aircraft multiplied by the load factor is going to come one half of it on each end of the wing. Or if it's mono wing, which is essentially you're talking of the entire wing being a single structure instead of two half wings, so starboard and port, joined to the fuselage, then you are having very, very large load. But now, if you're breaking up that area, because the wing loading is what is important, the overall lift that to be generated divided by the area of the wing platform area. So now, if you're dividing that into two, you have two different attachment points, and the loads which are coming are also reduced. So, but because of the fact that it had aerodynamic inefficiency, beyond a point you could not use it when you wanted to fly much faster, or you wanted to fly much bigger airplanes with more people in it or more cargo in it. So either when size or the speed or performance requirements went up, those were seen to be fairly inefficient designs, so you had to move on. So the point that you brought out in the context of it being a fail-safe design, yes, absolutely true. So let's say of the biplane, one of the wings want to fail. With the other wing, probably very, very expert pilot who might be able to maneuver it and probably land it. So you had at least a remote chance where you could probably save lives or major part of the aircraft. But that doesn't exist in the case of the single wing. But the way the attachments have become fail-safe or redundant is in a different sense it's being taken care of. So yeah, so that's as far as those are concerned. Then which we talk about mechanical engineering. Of course, there are machines and various other structures, but because we're talking of aerospace engineering, where we're talking of moving bodies, let's talk of moving bodies which are typically designed by mechanical engineers, usually by automotive engineers, but I'm sure the body of knowledge which is required to do that is very similar. So now in terms of mechanical engineering, on the surface vehicles and the flying vehicles, what are the differences in terms of materials, geometry, loads and design to try to touch upon? So what are the typical materials which are used for, let's say, a car, or let's say to build a train or to build a ship, and can those materials be used on large scale on an aircraft or a helicopter? Any mechanical engineers? Right. Right.
You can sell the material, but however, the usage is less. Because of the ease of manufacturing, ease of machining is one factor that affects the use of it.
Right. So that's one difference from a material sense. Any other differences from a materials point of view? What is used on surface vehicles as opposed to flying vehicles?
Working temperature changes, space, materials required to naturally lower that kind of.
Excellent. Yeah, very, very important point. So far we've been discussing purely mechanical properties like strength, stiffness, density, etc. But many of the loads are not just mechanical but also thermal loads. And as you know, typical aircrafts will cruise at a few kilometers above the ground level, so the temperatures that they are exposed to are much lower over there. If there are components very close to the engine or within the engine, then very high temperatures, especially go to the combustion chamber or beyond to the turbine blades or the nozzle. So those portions will require certain very, very stringent thermal requirements because the thermal stresses are very, very large. So excellent point brought out by him. Whereas you may not experience that such high temperatures. Still in IC engines and things like that, you might have certain small structural components facing very high temperatures, but compared to the stringent requirements we have for aerospace, with an additional requirement that it be very light, makes it even more complicated, especially to design materials for high temperature applications, where they are not just facing those high temperatures, but they are also mechanically loaded. So it's happening simultaneously. So if it's still within the elastic limit, we have a new body of knowledge instead of elasticity, we are talking of thermoelasticity, and that's a big area of research as well. And then you bring in the other aspects, so that combines your other force mechanics and thermodynamics of propulsion with the light vehicle structures. Similarly, when you combine the fluid dynamics with the structures, you have another body of knowledge called aeroelasticity. So if you combine the controls, for those of you in the double background, so you combine the electrical, electronics or computer aspect of it with it, you get what is known as the servo-elasticity, where you're talking of the control system structure interaction with each other. And typically, what really is required in an industry eventually for the final design stages at least is aerothermo servo-elasticity. So you're basically combining all those four streams which are studying separately over here and seeing how they interact with each other. In earlier days, it used to be quite simple to do that. You have compartmentalized education and they all came together and did it. But because what is known as the principle of superposition was valid because you're operating within linear regimes as far as the loading is concerned in different streams. So when you combine these, develop each one of these separately and then combine it, it worked fine. But now we are pushing the limits in terms of the aircraft performance requirements, be it the speed, the kind of maneuvers it can do, the kind of payload factors it can have, which is the payload weight divided by the overall weight, the range that it has to fly. In the case of other missions like drone, for example, doing a reconnaissance, or a let's say a fighter doing a reconnaissance mission. The endurance is very important, how long it can stay in the air before it can land. So all of these becoming critical means that the requirements in terms of the materials and other things also are large, and the non-linear aspects of each one of them comes into prominence. Because when you're stretching the limit in structures, for example, you're going in beyond that fact that E is a constant. The stiffness that we're talking about, which we defined as the slope of this strain curve, is no longer a constant. It can vary with the strain. As the strain increases, this E changes. So that's a non-linear behavior from a material point of view. The other aspect we have is thin-walled structures, because these structures are so thin that they deform so much. In fact, you would have seen if you are sitting on a window seat in an aircraft or a passenger aircraft when you're flying, you would have seen by the time it takes off how much the wing tips are moved up. So the kind of deformations that are involved are fairly large, and with these large deformations, what is known as the strain displacement relationship becomes nonlinear. So earlier in answering your question, I talked about strain, the normal strain as just a change in length divided by original length, right? So that definition may not no longer hold good, because you would have much more complicated, higher order derivatives of the displacement with respect to the coordinate along which the deformation is taking place will become more and more significant, and so those have to be taken into account as well. So these material and so-called geometric non-linearities, etc., will start playing a very critical role, and then principle of superposition will not work, because you don't have linear models within each one of these. So you cannot just develop each one of them separately and then combine. You have to develop them upfront right from the beginning, all taking into account all these couplings, because these couplings can be highly nonlinear in nature, and therefore the kind of phenomena which is observed from an overall nonlinear development will be very, very different from what it is from separate systems and then combining these. So we just have about 7 minutes, so just introduce ourselves. There are TAs. Can you just stand up or raise your hands? Phanendra, Rajesh, and Shraddha, Okay, so we have 4 PhD students from our lab. Rajesh and Phanendra over here. Phanendra at the back, you can see them over there. And Rajesh is over here in this corner. Very similar kind of dresses. It's not a uniform for the PhDs. So these 4 people will always be available on this particular email address, common email address for all 4 of them, specifically for this particular course related interactions. Of course, you can email me also, but you can see that a lot of things can be clarified with them. They will be handling all your assignments that you're submitting, and the tests and other things, and a few other things. So you're always very, very resourceful in terms of contacts. As you know, we already have a Microsoft team dedicated to this particular course. So maybe they can upload certain resources as and when required in terms of the kind of assignments and or tests that are following. So if any needs like that are there, just sound them out, and they'll be open to you. Next, in terms of the name of our lab, it's very important. You see why I was talking about nonlinear for so long, a little bit of bias from my own research area being in nonlinear materials, nonlinear geometric behavior, etc. So this is the lab. We have the first floor of this same building, and we also have my office in the same next door to the lab. And what we work on are not just the nonlinear aspects from a mathematical point of view, but in terms of going to what are known as futuristic composites for the, let's say, 10-20 years down the line for application in aerospace and non-aerospace scenarios as well, where the material that is used is not only doing load bearing in the sense of providing a certain amount of stiffness, a certain amount of strength, a certain amount of stability, a certain amount of thermal capability, as they pointed out, but also maybe a few other things. The structure itself, for example, doubling up as a battery in an electric vehicle, or the structure itself doing sensing and actuating. Many of you would have heard of the concept of smart structures. So where the structure is smart enough to adapt to new environments, and that all of that is bio-inspired. Our body, it goes to a colder place, it goes to a hotter place, it goes to a rainy place, etc. It tends to adapt to those situations, or you go to different time zones after probably a little bit of a jet lag, or whatever, you try to adapt to those situations. So that adaptation to the ecosystem is very, very essential for survival of biological specimen. Right from human beings all the way to bacteria, etc. They tend to adapt, and that's the reason why it's so difficult to handle pandemics like COVID, etc. Because they mutate, and you would have different kinds of behavior which may not be addressable by the techniques that we used earlier. So we try to bring in some of those functionalities. I mentioned sensing, actuation, energy storage, which is like battery, etc., and many other things that we think of, electromagnetic functionalities, etc. So if we can combine that, the advantage is that the reason why we went from let's say wood and fabric eventually to metals and lighter metals, aluminum alloys, etc., many different categories, lighter and lighter aluminum alloys like lithium aluminum, where the primary alloying element along with aluminum is lithium, which is the lightest metal, as you know, in the periodic table. So now to composites. So the whole idea was to enhance these two factors, right? Specific strength and specific stiffness. Now, when you bring in multifunctionality, what happens is you're going one step further and probably eliminating another subsystem that you might have. Let's say, for example, the structure is doubling up as a battery. You don't need to take up another battery, or even if you had to for redundancy, fail-safe kind of a design, you would probably take up a much smaller or lighter battery than what you would otherwise. So similarly, in terms of sensing and actuating, when you're trying to do it online in real time, you are getting more and more efficient structures, because the efficiency of a flying vehicle could be different in different phases of flight. So a particular geometry, let us say, of the airfoil of the wing that we are using, this might be an ideal or optimal shape for cruise flight. But the same aircraft has to fly, has to take off, it has to climb, it has to probably do certain maneuvers depending upon what kind of aircraft it is, especially fighter aircraft. Then you want the shape to change. For example, in certain maneuvering situations, you might want a thinner airfoil or more camber that you want in the airfoil. Can you do that real time? As the aircraft changes from a cruise to a maneuver, can the shape of these change? So what we call as morphing. So can you do it with the kind of materials that you have so that you are much more efficient aircraft? Efficient aircraft means either you're burning less fuel, which is environmentally good, it is less cost to the operating agencies, it's an airline or whatever, and it could fly a larger range probably with the same amount of fuel, or you keep the fuel the same, you increase the payload, you can probably take a few more passengers and they will be paying for their tickets, and it's a better business proposition. So at the end of the day, economics plays a very, very critical role, the costing and the expenses that are involved, not just for the original aircraft, but eventually over its life cycle. Typical aircraft will last you for about 30 years. So passenger aircraft, some of the military aircraft might be used even longer, but also depends on the flying hours, etc. So in that period of 30 years, the amount of money that is invested by the owner, only 1/3 of it was the original cost of the aircraft. The other 2/3 typically goes for MRO, what is known as maintenance, repair, and overhaul. I'm not talking of fuel costs, etc. That is far, far bigger compared to everything. So that's operating cost, which is required in a certain way, but we're talking the capital cost. So because these components, even the fail-safe components, some of them have to be replaced in a certain regular intervals. And you are all familiar with, for your either your 2-wheelers or 4-wheelers, you see you have to go send it to the service station on a regular basis, and for a periodic maintenance, you have certain parts which have to be replaced, etc. So it's very similar in this context, just that things are much, much more rigid, and compliance is very, very important. Otherwise, you will no longer have the flight certification, it will expire, and you may not be able to fly your aircraft. It will be a dead investment that you have. So all of these aspects again and again we keep touching as and when necessary through the flow of our subject. So it is at 3:30, so we will conclude today's class. And if any of you have questions, you might feel free to stay back and ask, and the rest are free to leave. Thank you. I'm pressing right.